Hello, in this video, I'd like to demonstrate a proof by contradiction. A proof by contradiction is a type of indirect proof, where we take a direct argument, such as the cube root of 5 is not an element of rational numbers. We assume something false about it. For example, cube root of 5 is an element of rationals. Do a direct proof trying to prove that false statement, reach a contradiction in the proof, and thus prove that the original statement that we assumed false is actually correct. So in this proof, I'm going to demonstrate that the cube root of 5 is not an element of rational numbers through contradiction and the Euclidean argument. So first we have to assume something wrong with it. So we're going to assume that the cube root of 5 is actually an element of rationals, and that since it's an element of rationals, we can define it as there exists an A element of integers, and there also exists a B element of integers not equal to 0, such that cube root of 5 is equal to A over B. So this is by definition of rationals. We must also state that A and B have no common factors. This statement will directly lead to the contradiction we reach later on in the proof. So step 2, we manipulate some algebra. So by the definitions we set N1 and some algebra, we can show that cube root of 5 is equal to A over B, thus 5 is equal to A cubed over B cubed, and finally A cubed is equal to 5 times B cubed. Taking the algebra from 2, we show that 5 divides A cubed. This is because B is defined as an integer, and thus under closure of multiplication of integers, B cubed is also an integer. So 5 divides A cubed by definition of Euclidean division. Since 5 divides A cubed, it can also be assumed that 5 divides A by the lemma. The lemma is, in this case, that if 5 divides something cubed, then 5 will also divide that something. So let's just say that the lemma states that for all x element of integers, that if 5 divides x cubed, then 5 divides x. A is obviously an integer as defined in step 1, thus the lemma would apply here. Usually in a proof you're going to have to prove the lemma separately, but I'm not going to do it in this proof for sake of time, but just remember you cannot assume the lemma unless it's given to you and explicitly stated that you can assume it. So since 5 divides A cubed, then we can assume that 5 also divides A by the lemma. Knowing that 5 divides A, we can conclude that A is a multiple of 5. Thus we can define A as there exists a k element of integers, such that A is equal to 5 times k. By definition of Euclidean division. Having done this, we can plug this back into the original equation. So by step 2 and 4, we substitute some values to get 5k cubed is equal to 5 times b cubed. 5k being a, of course, and we're plugging it into a. So this gives us 125k cubed is equal to 5 times b cubed. Solving for b, we get that k cubed is equal to b cubed, getting rid that 25k cubed is equal to b cubed, and thus b cubed can be written as 5 times 5k cubed. Now 5k cubed can be taken to be some, let m equal to 5k cubed element of integers under, since integers are closed under multiplication and addition. Thus we can conclude that b cubed is equal to 5 times some m. Well, having shown that b is equal to 5 times some m, then b is also divisible by 5. By step 5, it is evident that 5 divides b cubed. Knowing that 5 divides b cubed, we can apply the lemma here again. So 5 divides b cubed means that 5 also divides b by the lemma. Since 5 divides b, we know that b is a multiple of 5. Moving on to the next step, we have shown that a is a multiple of 5 and b is also a multiple of 5. So we have reached a contradiction here. Since our first step, we stated that a and b have no common factors. So by steps 3, I believe, yes, by 3 and 6, a and b both have a factor of 5, and a common factor, 5 being this common factor. This is a contradiction of the things we have set down in step 1, so we end the proof here, having proven the original statement that the cube root of 5 is not a rational number through contradiction. So some of you may be wondering why, sure, we have reached a contradiction given everything that we have defined up here, but why can't a and b have any common factors? Well, this is easiest to show by plugging things back in. So we have shown that we have defined a as equal to sum 5k. Plugging this into a cubed equal 5b cubed, we get 5k cubed is equal to 5b cubed. Well, in step 6, here, we have also shown that b is a multiple of 5. Knowing b is a multiple of 5, we can also define b as some integer times 5. I'm just going to call it j. So let's say there exists a j element of integers such that b is equal to 5j. Well, plugging this into here, we show that 5k cubed is equal to 5 times 5j cubed. We do some algebra, getting 125k cubed is equal to 5 times 125j cubed. Well, the 125's cancel out, and we're left with k cubed is equal to 5j cubed. Does this look familiar? Of course it does. A cubed here is equal to 5b cubed, and k cubed is equal to 5j cubed. Thus, we can repeat the pattern, knowing that k cubed is written as 5 times some j cubed, j being some integer. As defined here, we can show that 5 divides k cubed, which means that 5 divides k. And so since 5 divides k, we can define k as there exists, let's just call this r, element of integers, such that k is equal to 5 times r. Plugging this back in, we get, plugging this back into this equation here, we get that 5r cubed is equal to 5j cubed. Notice how this looks similar to this expression up here? To this expression up here? If we say that a and b can have common factors, we're stuck in an infinite loop where we define a and b, or whatever derivative whatever other variable we've defined them as, over and over again. Thus, a and b can't have any common factors, or we're stuck in this infinite loop. That's why, in the first statement, we have to say a and b have no common factors. Otherwise, we just keep on infinitely proving something that goes on forever. And that's a proof of contradiction showing that the cube root of 5 is not an element of rational numbers through the Euclidean argument.